Hello everyone, welcome back to Deviations. In this video, I would like to finish off our little mini unit on the disk and shell method of solids of revolution by covering a really challenging example comparatively with the shell method. So as we know, the shell method is the method where we take cylindrical shells and we rotate them about axes to find solids of revolution. Well, we are now going to kind of mold something that we've done in areas between curves, and we're going to bring it over to the shell method just as we did with the disk method. So what we do is we remember how sometimes we can have these curves like parabolas or trig functions or linear functions, and we can find the area between these curves by determining intersection points, determining which is on top, and then determining the area in the region. Well, now we are going to consider what happens if we find that region and we rotate that about an axis in order to find the volume of a solid of revolution. So we will look into that in this video. Alright, so let's take a look at our example here. So for this example, I would like to rotate the region bounded by x plus y equals 4, and x is equal to y squared minus 4y plus 4. Now, something that is important is that we need to remember that we are now going around the x-axis. So in terms of disk and shell, that means that we're really going to need to think about integrating over y. So we'll have y differentials as opposed to x differentials. The other thing that we need to consider is we need to consider that some of our functions here are not in explicit form. We need x to be isolated on one side so that we can easily solve for our zeros. So with that said, why don't we get started with that? Okay, so what we are going to do now is we are going to find our points of intersection. So to find our points of intersection, we need to set these curves equal to one another, which means for the first curve, x plus y equals 4, isolating the x variable. Okay, so what we do is we isolate the x variable, we set it equal to one another, and then we are left with a quadratic equation that says that y squared minus 3y is equal to 0. Factoring that, we can take a y out, and that gives us y times y minus 3 is equal to 0. And then we can easily see that our zeros of this are going to be 0 and 3. Okay, so now we know what we are integrating over. So what I would like to do now is I would like to draw what we are going to be performing. So here is our y-axis and here is our x-axis. Now what we need to do first is we need to draw our curve. So drawing our curve means that we are probably first going to want to draw this linear equation. So we're given 4 minus y is equal to x. So we are going to have an x-intercept of positive 4 and a y-intercept of positive 4. And we are going to have a slope of 1. So we're going to be coming in like this. And that is what our curve there looks like. The other thing that we know is where our curves intersect. So we know that they intersect at y is equal to 0 and y is equal to 3. So we have 1, 3 here. So now we can kind of see that our parabola is going to look something like this. And there's our parabola here. So we're going to be taking this region in here, and we're going to be rotating this region about the x-axis. Okay, so now we are prepared to take a look at our actual integration. So we know that we need to find our r and our h because of our formula for finding these areas. So our r is going to be equal to y. That's what our radius is equal to. Now our height is going to be equal to the difference of the function. So we know the linear function is on the top and the quadratic function is on the bottom. So that means that we set the height equal to 4 minus y minus open parenthesis y squared minus 4y plus 4 close parenthesis. And when we do that math out, it turns out to be 3y minus y squared. Okay, so now we are prepared to perform our integration. We know that the volume is equal to the integral between our endpoints, which in this case are 0 and 3, 2 pi rh times our differential, which in our case is dy. We can rewrite this as the integral between 0 and 3 of 2 pi times y times 3y minus y squared with respect to y. Next, we can pull out that 2 pi, giving us the integral of 0 to 3 of 3y squared minus y cubed dy, all times 2 pi. That gives us 2 pi times y cubed minus 1/4 y fourth, evaluated between 0 and 3. Alright, so now all that's left is to apply this fundamental theorem of calculus, and this is going to give us the volume being equal to 2 pi times 3 cubed minus 1/4 3 to the fourth, which is equal to 27 pi over 2. Thank you very much for watching this video of 3 deviations, and in the next video we're going to be moving on to some physics applications looking at work integrals. If you're taking an AP Physics C class or a Physics 1 class, you'll probably have been introduced to work integrals. We're going to be looking at that in the next video. We'll see you guys then.